Picture for a moment the dry places of our world seen from very high above, where the curve of the earth softens into pale gold, and the great deserts spread like quiet seas of sand. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From that height, the deserts of the planet look almost still, almost sleeping, as if the wind had paused to think. Roughly 1/3 of all the land on Earth is dry. Not just a little dry. So dry that rain is a rare guest, sometimes arriving only once in a year, sometimes once in a decade. These wide regions stretch across every continent. They wrap around the warm middle of the globe in two pale bands, and they hide in the cold, high plateaus, and they cling to the shadow side of tall mountains, where the clouds give up their water before they can cross. The Sahara alone is nearly the size of the United States. The Gobi rolls across cold stone plains in Asia. The Atacama in South America holds places where rain has not been recorded in living memory. The Australian outback glows red beneath a wide and patient sky, and in the south of Africa, the Kalahari and the Namib sit side by side, ancient and strange, with dunes that meet the cold gray Atlantic in a slow line of foam. Seen from far above, these lands look empty. That is the first quiet mystery. They are not empty at all. Beneath the surface, inside the cracks of stones, under the hot crust of sand, and within the dry stems of small plants, life is going about its long and patient work. Beetles wait out the heat in shallow burrows. Seeds rest in the soil for years, holding their breath, waiting for a single good rain. Microscopic crusts of bacteria, algae, and fungi grow as thin, dark skins across the open ground, breathing slowly, fixing nitrogen, holding the desert together one grain at a time. The scale of this hidden world is hard to hold in the mind. Picture an area larger than a small country, where almost nothing seems to be alive. And then imagine that under every square meter of that ground, dozens of tiny living things are quietly surviving. They have done this for thousands of years, and in some places, for millions. This is where the open question begins. We still do not fully understand desert ecosystems hold themselves together. We know many of the pieces. We know how a cactus stores water. We know how a sidewinder snake moves over hot sand. We know how a fog-drinking beetle tilts its body to catch droplets on its back. But the whole picture, the way all of these patient strategies fit into one working system, is something scientists are still slowly piecing together. Each new study seems to add a small surprise. Each dry valley seems to hide one more creature, one more trick, one more way of staying alive on almost nothing. There is something almost meditative about looking down on these lands from above. The dunes form long ripples, like waves frozen mid-roll. The dry riverbeds, called wadis or arroyos, wind across the plains like the veins of a sleeping animal. Salt flats shine white under the sun, flat as glass. Ancient stones, carved by wind for ages, stand alone in wide, empty plains, casting long shadows in the late light. It is easy to think of the desert as a hard place. It is in many ways, but it is also a quiet place, a slow place, a place where time moves at a different speed. A rock here may take 1,000 years to crack. A creosote bush may live for 10,000. Seeds may sleep for decades in the soil, perfectly still, before opening into flowers after a single soft rain. Over the next many hours, we will wander gently through these dry lands together. We will sit with their mysteries. We will look at the questions that remain open, the theories that researchers still argue about quietly in their papers, and the small wonders that no one has yet fully explained. We will not rush. We will not try to solve everything. We will let the dunes do what dunes do, which is to shift slowly under the wind while the stars wheel overhead. For now, simply rest in the image of those pale lands, vast and quiet, holding their secrets close, and let your breathing slow to match the long, patient rhythm of the desert itself. So what, in the simplest terms, is a desert? The answer is gentler than you might expect. A desert is not, at its heart, a place defined by heat. It is not defined by sand, nor by sun, nor by the rolling dunes we so often picture. A desert is defined by something much quieter, by absence, by the simple fact that very little rain falls there. The standard most scientists use is this: a desert is any place that receives less than 10 inches of rain in a year. 10 inches. About the height of a dinner plate stood on its edge. If you imagine the rain that falls on a soft green meadow in spring, gathering in puddles, soaking into the soil, filling the streams, a desert receives only a small fraction of that amount across an entire 12 months. Some deserts receive far less. Parts of the Atacama in South America may go years, sometimes decades, without measurable rain at all. That single fact shapes everything else. The plants, the animals, the stones, the silence. Aridity is the architect. Heat is only a guest. This is why scientists draw the boundaries of a desert by water, not by temperature. A desert can be scorching, with daytime air that shimmers above the sand. A desert can also be freezing, with winds that cut across frozen ground and snow that falls but rarely melts. Antarctica, by this measure, is the largest desert on Earth. Its dry, cold interior receives almost no precipitation at all. The vast white plateau, larger than the United States and Mexico combined, is technically the driest continent we know. Taken together, deserts cover roughly 1/3 of the land surface of our planet. Imagine standing on any random patch of dry ground on Earth. There is nearly a 1 in 3 chance you are standing in a desert. That share has shifted across deep time, growing and shrinking as climates have changed. But the rough proportion holds in our current age. 1/3. A quiet, sweeping presence that we often forget about because so few of us live within it. The largest hot desert, the Sahara, stretches across northern Africa for about 3.5 million square miles. That is nearly the size of the entire United States, set down across a single continent. Within it lie dune fields larger than many countries, mountain ranges of bare stone, and salt flats so flat that the curvature of the earth becomes the only horizon. The Gobi in Asia, the Australian outback, the Arabian desert, the Kalahari, the Sonoran, the Patagonian, the Karakum. Each one its own world, and each one bound by the same quiet rule of too little rain. The age of these places is harder to fix, and this is where the first soft mystery begins. Some deserts are very young, only a few thousand years old, shaped by recent shifts in wind and weather. Others are ancient beyond easy imagining. The Namib, along the southwestern coast of Africa, is thought by many researchers to have been arid for at least 55 million years, possibly far longer. Other scientists suggest the true number is closer to a few million, with wetter pauses in between. The evidence sits in old sands, in fossil pollen, in the patterns of stone. The question of just how old the world's driest places really are remains open. What a desert is made of varies, almost as much as where it lies. The image of endless sand is, in truth, a small part of the story. Only about 20% of the world's desert surface is covered in sand dunes. The rest is something else entirely. Bare rock polished by wind. Gravel plains, sometimes called redge, where small stones lie packed together like a stone mosaic stretching to the horizon. Dry riverbeds, salt crusts, hardened clay, low, scattered shrubs spaced widely apart, each plant claiming a patient circle of root space beneath the ground. The composition tells you something about the desert's history. Sand grains were once mountains, ground down across millions of years. Gravel plains were once seabeds or river deltas. Salt flats were once shallow lakes, slowly evaporating, leaving their minerals behind in pale, glittering sheets. Every desert is, in a sense, a memory of water that was once there and is no longer. Holding all of this in mind, a desert begins to feel less like an empty place and more like a long, slow story. A story told in small rainfall, in deep time, in the patient rearrangement of stone and sand. Before we ask how the desert is born, it helps to remember what it truly is. A place defined by what is missing, and, as we will see, by what quietly endures inside that absence. Not every desert is born the same way. They look alike from a distance, all quiet and dry and golden, but their origin stories vary in surprising ways. Some deserts are old beyond easy imagining, while others are still forming, year by year, in places that once held water. To understand how a desert comes to be, we have to slow down and look at the many faces of aridity each shaped by a different patient force. The most common kind of desert sits in a band that wraps around the planet, roughly 20 to 30 degrees north and south of the equator. These are the great subtropical deserts: the Sahara, the Arabian, the Kalahari, the deserts of Central Australia. They exist because of the slow churning of the atmosphere itself. Warm, wet air rises near the equator, climbs high into the sky, dumps its rain over the tropics, and then drifts north and south as dry, descending air. By the time that air sinks back down, it has lost almost all its moisture. It arrives at the ground warm and thirsty, ready to pull water out of the land rather than give any back. These belts of sinking air paint the planet with sand. A second kind of desert hides in the shadow of mountains. When wet air drifts in from an ocean and meets a tall mountain range, the air is forced upward. As it climbs, it cools. As it cools, it cannot hold its water, and the rain falls on the mountain's windward side. By the time the air crests the peaks and tumbles down the other slope, it is dry, warm, and starved of moisture. The land below sits in what scientists call a rain shadow. The Gobi lies behind the Himalayas. Parts of Patagonia lie behind the Andes. The Great Basin of North America lies behind the Sierra Nevada. The mountains do not mean to make deserts. They simply stand in the way of the rain, and a dry world unfolds in their wake. Then there are the coastal deserts, which seem to break every rule. These dry lands lie right beside the sea, where you would expect rain to be easy. Yet the Atacama in Chile and the Namib in southern Africa are among the driest places on the planet. The reason is the water itself. Cold ocean currents sweep along these coasts, chilling the air just above the waves. Cold air cannot lift much moisture into the sky, so the fog rolls in thick and gray. But the rain almost never falls. The Atacama has places where no measurable rain has been recorded for centuries. The ocean is right there, gleaming, and still the ground stays dry. A fourth kind of desert is shaped not by latitude or mountains or currents, but by sheer distance from the sea. These are the continental deserts, locked deep inside vast land masses where no moist wind can reach. By the time any ocean air arrives, it has traveled so far across land that it has nothing left to give. Central Asia holds many of these. The middle of Australia, too, where the heart of the continent simmers far from any coast. And there is a fifth face of aridity, often forgotten. The polar deserts, Antarctica, and parts of the high Arctic receive almost no precipitation at all. The air there is too cold to carry much water. The ground is locked in ice, but ice is not the same as wetness. By the strict definition of a desert, which is simply a place that receives very little precipitation, these frozen lands qualify. We will return to them later in their own quiet section. What remains genuinely open, what scientists still puzzle over, is how stable any of these deserts truly are across deep time. The Sahara, for instance, has not always been a sea of sand. Cave paintings and fossil riverbeds show that only a few thousand years ago it was green, dotted with lakes, alive with hippos and crocodiles, and people who fished its shores. Then, gradually, it dried out. The cause is debated. Some researchers point to slow wobbles in Earth's orbit that changed how sunlight fell on the continent. Others wonder whether vegetation loss and changing winds tipped the system from green to gold. The transition may have been slow, or it may have come in sudden lurches. The full story remains unsettled. Each desert, then, carries a different birth story written into its sand and stone. Some were forged by the breath of the planet itself, others by mountains, or cold seas, or simple distance. And some, it seems, were born more than once, drying and greening and drying again across the long ages. A desert is built less from what is there than from what is missing. The missing thing is rain. To understand a desert, we have to think about water itself and where water came from in the first place. The story is older than the sand. It is older than the wind. It reaches back to a time when the young earth was a hot ball of melted rock with no oceans at all. The water in every dry riverbed, every hidden spring, every small drop of dew on a thorn began somewhere out beyond our world. Scientists still debate exactly how. One idea is that water came riding in on comets, those slow, icy travelers from the cold edges of the early solar system. Another idea is that much of it arrived inside asteroids, locked into the minerals of small rocky bodies that crashed into the young planet. A third possibility is that some of the water was here from the very start, baked into the dust that formed the earth. The truth may be a mix of all three. We do not yet know the exact recipe. What we do know is that water is a strange and patient traveler. The same molecules that now sit deep beneath a desert have been here in some form for billions of years. They have been ocean. They have been ice. They have been breath inside the lungs of long-vanished animals. And in a desert, those same molecules are simply, for a long while, somewhere else. They are over the sea. They are locked in distant clouds. They are falling on a green valley 1,000 miles away. The air above a desert is not empty. It is full of gases, mostly nitrogen and oxygen, with small amounts of argon, carbon dioxide, and traces of water vapor. In a wet place, that water vapor gathers, cools, and falls. In a dry place, it stays aloft, thin and high, refusing to come down. The reasons are mechanical. Warm air can hold more moisture than cool air. When warm air sinks, it grows even warmer, and its grip on water tightens. Rain becomes a memory rather than an event. The sand itself has its own deep story. Most desert sand is made of quartz, a hard mineral born from silicon and oxygen, two of the most common elements in the Earth's crust. The grains began their lives as part of mountains. Over many millions of years, rivers and frost and wind broke the mountains down, carrying their fragments to lower ground. The softer minerals dissolved or crumbled into clay. The quartz, stubborn and patient, remained. What you see when you look at a dune is, in a sense, the skeleton of mountains that no longer exist. Iron gives many deserts their warm color. The red sands of certain old dunes, the rust of certain canyon walls, all come from iron compounds that have slowly reacted with the thin moisture in the air. That iron itself has a far older origin. Every atom of iron in the Earth's crust, in the Earth's core, in the blood of a desert lizard, was forged inside a dying star long before our sun was born. When collapsed and scattered its insides across space, the iron drifted out into clouds of dust and gas. Some of that dust gathered to form our planet. The red of a desert evening is, in a quiet way, the light of an old star reflected back. Salt is another building block of the Drylands. Where ancient lakes once stood, the water has long since evaporated, leaving behind wide white flats of salt and other minerals. These flats hold a record of vanished seas and forgotten rains. Some are thousands of years old. Some are much older. Walking across them, a person crosses the dried bones of water that fell when the world looked very different. There are still open questions about why some regions remain dry for so long. The big patterns of sinking air and cold ocean currents explain a great deal. They do not explain everything. Some researchers wonder whether small shifts in the tilt of the Earth or slow changes in ocean temperatures may push deserts to grow or shrink over thousands of years in ways we have not fully mapped. The records held in salt layers, in old pollen, in the rings of ancient trees on the edges of dry lands, are still being read. A desert, then, is made of star-forged iron, of mountain bones, of vanished seas, and of air that has, for now, forgotten how to let go of its water. The missing rain is itself a piece of the puzzle. Where it has gone and why it stays away is part of the long mystery we are still slowly unraveling. Sand is one of the strangest materials on Earth. It looks soft and simple, but it behaves in ways we still do not fully understand. A single grain may be smaller than a poppy seed, yet trillions of these grains together can build mountains taller than skyscrapers. They can flow like water. They can hum like distant music. They can swallow ancient cities, and then, centuries later, give them back. The forces that move sand are mostly invisible. They are the slow, patient sculptors of the dry world. Wind is the first of these forces. In the desert, the air does not move like it does over a forest or a sea. The ground heats quickly under the bare sun, and that heat rises in tall, shimmering columns. Cooler air slides in to take its place. This back and forth, hour after hour, creates steady currents that brush the surface of the sand. Grains grains begin to roll. They tumble forward, bouncing in tiny arcs, knocking other grains loose as they land. The science of this small bouncing dance has a name, saltation, which simply means the leaping motion of grains across the ground. From these tiny leaps, great shapes are born. A dune is not a fixed thing. It is a slow river of grains, always moving, always reforming. The wind pushes sand up one gentle slope, lifts it over a sharp crest, and lets it slide down the steeper side. Bit by bit, the whole dune creeps forward, sometimes only a few feet a year, sometimes much more. Over centuries, a dune the size of a small hill may travel many miles. The dune you see today is not the dune that was there 100 years ago, even though it looks the same. Different winds make different dunes, where the wind blows steadily from one direction. Long curved dunes called barkhans form, with horns that point downwind. Where winds blow from many directions, star dunes rise with several arms reaching out from a central peak. Some star dunes in the Sahara and in the deserts of Iran are believed to be tens of thousands of years old. They stay roughly in place while sand swirls around them. How they remain so stable for so long is still a puzzle that researchers are working to understand. There is another strange thing sand can do. In certain deserts, when a person walks down a steep dune, the sand begins to hum. The hum can deepen into a low, droning note, almost like a cello played far away. Travelers have reported this sound for centuries. The booming dunes of the Mojave, the Namib, the Gobi, and parts of the Arabian Peninsula all produce these sounds, sometimes loud enough to be heard miles away. Scientists have a few ideas about why. One idea is that the grains, when they are very dry and very smooth, slide against each other in synchronized layers, and the friction creates a vibration that travels through the whole dune face. Another idea points to a thin coating of silica or other minerals on the grains, which may help them vibrate at a shared frequency. The exact recipe for a singing dune is still debated. Not every dune sings, and even dunes that do sing sometimes fall silent for years. Gravity also plays its part. Sand can only pile so steeply before it slumps. The angle at which which it gives way is remarkably consistent, about 34 degrees in dry sand. This is called the angle of repose, and it is one of the reasons dunes have such smooth, similar shapes across the world. The wind builds the windward slope gently, but gravity sets the limit on the slip face behind. Push past that limit, even by a single grain, and a small avalanche begins. These tiny avalanches are part of what makes dunes hum. Heat squeezes the picture in subtler ways. By day, the surface bakes. By night, it cools fast. Grains expand and shrink over thousands of years. This slow breathing helps weather the larger rocks of the desert into the very sand the wind will later carry. Every dune you see is, in some sense, the ground sea of a much older landscape that has been ground down, lifted up, and resettled by forces too slow to watch. What remains open is how all these forces fit together in detail. Why some dunes sing and others stay silent. Why some star dunes hold their shape across ages. The sand is always moving, always speaking in its quiet way, and we have only begun to listen carefully. For tonight, it is enough to picture those grains, drifting, leaping, settling under a wide and patient sky. Picture a single grain of sand. It is smaller than the head of a pin, lighter than a breath, almost weightless in the palm of your hand. Now picture the wind picking up that grain, lifting it from the floor of the desert, and carrying it forward at roughly the speed of a person walking. One grain alone does almost nothing. It cannot scratch a window. It cannot dent a stone. It is simply a tiny piece of broken rock drifting through dry air. But the desert does not send one grain. The desert sends trillions. In a single strong sandstorm, the air near the ground may carry millions of grains through every square meter, every second, for hours at a time. Each one strikes the rocks in its path with the soft tap of a fingernail. Tap, tap, tap. Over a year, a stone standing in the path of those winds may be struck by more grains than there are stars in the visible night sky. Over 1,000 years, the number climbs past anything the human mind can really hold. And the desert has had not 1,000 years, but millions. This is the scale of wind carving in the dry lands. It is the scale of patience. Consider a yardong, one of those long, sleek ridges of rock that rise from the floors of deserts in places like Iran, China, and the dry valleys of Antarctica. A large yardong can stand taller than a 10-story building and stretch longer than a football field. Its sides are smooth, almost polished, as if a sculptor had spent years running soft cloths over the stone. And in a sense, one did. The sculptor was the wind, and the cloth was nothing but tiny grains, year after year, age after age, to shape a single large yardong. The wind may have worked for 2 million years. If you turned each year into a single second, you would still be waiting for the sculpture to finish more than 3 weeks later without sleep. Or consider the ventifact, a smaller stone with faces ground flat by the prevailing wind. Some sit on desert pavements, no bigger than a loaf of bread. Their flat sides meet at sharp ridges, like the cut faces of a gemstone. A ventifact the size of your fist may have taken 50,000 years to reach the shape it has now. 50,000 years to polish something you could carry home in a coat pocket. The numbers grow stranger the closer you look. A grain of quartz sand, the most common kind in many deserts, weighs about as much as a single eyelash. To wear away just 1 cubic centimeter of solid sandstone, a cube small enough to balance on your thumbnail, the wind must deliver, by some estimates, billions of grain impacts. And that is for soft stone. For harder rock, granite, or basalt, the count climbs higher still. Yet the desert delivers. It always delivers. The wind never tires, never takes a day off, never asks for payment. The mystery, the part still being puzzled over by researchers who study these dry places, is exactly how the shaping happens at the smallest scale. We can see the sculptures. We can measure the wind. We can count the grains in the air. But the precise dance between a moving grain and a fixed stone, the way each tiny strike either chips, scratches, or simply bounces off, is still being studied in wind tunnels and computer models. One idea is that most of the carving happens within the first meter above the ground, where saltating grains, the ones that hop along the surface like skipping stones, strike with the greatest force. Another idea is that finer dust, suspended much higher, plays a bigger role over very long timescales than anyone first guessed. The full picture remains open. What is not in doubt is the scale of time involved. If you compressed the carving of a single great desert mushroom rock, those stones balanced on slender stems, wider at the top than at the base, into the length of a human life, then a human lifetime would be 1.5 seconds long. Everything you have ever done would happen between 2 heartbeats of the stone. Stand near such a rock at dusk, and you stand near something that has been shaped by a process slower than memory, slower than language, slower than our species. The wind is still working on it. Tonight, somewhere in a dry land far from any city, a single grain is lifting off the sand, drifting forward, and touching a stone for the first and only time in its small life. Tap, and the sculpture continues. Imagine standing on the crest of a great dune at sunrise. The sand beneath your feet glows in soft shades of apricot and rose. The wind has carved long ripples into the surface, fine lines that curve like the grain of polished wood. In every direction, the dunes roll away in slow waves, some sharp-edged, some smooth as sleeping animals. The air is dry and still. Nothing moves. Nothing seems to live. And yet, somewhere far below your feet, there may be water. Cold, dark, ancient water, resting in stone. This is one of the gentler mysteries of the desert. A place that looks utterly dry on top can hold enormous amounts of water deep beneath the sand. These hidden pools are called aquifers, underground layers of rock or gravel that hold water in their tiny spaces, the way a sponge holds liquid. Some of these aquifers are small, others stretch for hundreds of miles beneath the driest places on Earth. The largest known one lies beneath the Sahara. It is called the Nubian Sandstone Aquifer System. It sits below parts of Egypt, Libya, Sudan, and Chad. The water inside it is not new. Much of it fell as rain tens of thousands of years ago, when the Sahara was green. Lakes shimmered there. Rivers ran through it. Grass grew tall, and herds of animals moved across plains where today only sand remains. The rain from that long ago whirled soaked down into the rock there, locked away, while the surface above slowly dried into the desert we see now. Picture it for a moment. You are standing on warm sand. Beneath your boots, beneath the dune, beneath layer after layer of stone, sits water that touched the open sky before the first cities were built. Water older than writing, water older than the wheel. How much of it is left? No one truly knows. Scientists can drill test wells. They can measure the water table in certain spots. They can use satellites that sense small changes in gravity to estimate how the underground water is shifting. But these are estimates. The aquifers are vast and uneven. In some places, the water sits close to the surface. In others, it lies far down in deep stone chambers that have never been mapped. The full shape of these hidden seas remains an open question. And there is another puzzle. In some deserts, the water down below is not entirely still. It moves very slowly through the rock. A drop might travel only a few feet in a year, but over thousands of years, this slow drift carries the water in long, quiet currents beneath the sand. Where exactly it goes and how the different aquifers connect is something researchers are still trying to understand. Some believe certain desert aquifers are linked across vast distances. Others think they are mostly separate, each one a sealed pocket of memory. On the surface, the only hints of this hidden water are rare and precious. Now and then, the underground layer rises close enough to the top that a spring breaks through. A small pool appears in a hollow between the dunes. Reeds grow around it. Palms lean toward it. Birds come to drink. These are the oases, green islands in a sea of sand, each one a window into the deeper world below. From above, an oasis looks like a small dark jewel set in pale gold. From the ground, it feels like a quiet miracle. Some oases have lasted for thousands of years. Others appear and disappear as the underground water shifts. There are stories of springs that ran for centuries and then went silent. There are also new springs that have opened in places no one expected. The desert keeps its own schedule, and the surface only shows a small part of what is happening beneath. What we do not fully know is how long this hidden water will last. In regions, people are now pumping it up faster than nature can replace it. Since much of the water is ancient, it does not refill quickly. Once it is gone, it may be gone for a very long time. Just how much remains, how it is shared between countries, how it connects to the climate of the past. These are all questions still being studied, still being argued over in quiet rooms full of maps. For now, the dunes keep their secret. They lie in the moonlight, smooth and silent. The wind moves their surface grain by grain. And far below, in the cool dark of the stone, the old water waits. It does not hurry. It has been waiting a long time already. In the driest places on Earth, where rain may not fall for years at a time, certain plants have found a quieter way to drink. They do not wait for storms. They do not send long roots down to hidden water. Instead, they reach up into the air itself and pull moisture from the thin morning fog. This is one of the strangest survival tricks in the natural world, and parts of it still puzzle the people who study it. Consider the coastal deserts along the western edges of South America and Southern Africa. These are some of the driest lands on the planet. Some spots in the Atacama Desert have gone decades without measurable rain, and yet, on certain mornings, a soft gray fog rolls in from the cold sea. The fog drifts low over the rocks and sand, carrying tiny droplets too small to fall. For a few hours, the desert becomes silver and damp. Then the sun climbs higher, and the fog vanishes like a slow breath. In those few quiet hours, life happens. Plants called tillandsia, sometimes known as air plants, gather the moisture directly through their leaves. They have no real roots in the soil. They simply lie on the open ground or cling to rocks, soaking in the fog through tiny scaly hairs called trichomes. Each hair acts like a small cup, opening when wet and closing when dry. The plant drinks the fog, then waits, sometimes for weeks, until the next gray morning arrives. Other desert plants have evolved different tools for the same quiet work. In the Namib Desert, along the southwestern coast of Africa, a low shrub called the welwitschia spreads two long, ribbon-like leaves across the ground. These leaves can live for more than 1,000 years. Some welwitschia plants alive today were were already old when medieval cathedrals were being built. Researchers have long wondered how the Welwitschia survives in a place that sees almost no rain. One idea is that the plant absorbs fog through tiny pores in its leaves. Another suggests its deep roots tap into ancient groundwater far below. The truth may be both, working together. The question remains partly open. The Namib is also home to grasses and lichens that turn pale white during dry months and bright green within minutes of being touched by fog. Lichens are not single plants, but partnerships, a slow marriage between a fungus and an algae. In the desert, they grow on rocks, on bones, on old wood, sometimes on each other. They drink the fog and store it inside their cells. Some lichens here may be thousands of years old. They grow so slowly that a patch the size of a dinner plate can represent more than a century of patient sipping. The big puzzle is how these plants survive the long stretches between fogs. A Welwitschia leaf in full sun can reach temperatures that would cook most living tissue. The lichens can dry out so completely that they appear dead, then return to life within seconds. Somewhere in their cells, a quiet chemistry keeps them safe. Scientists have studied special sugars and proteins that seem to protect the cells from collapsing as they shrivel. But the full recipe is not yet understood. How a plant can essentially pause its own life, sometimes for years, and then resume without damage, is still one of the soft mysteries of dryland biology. There is something gentle about imagining these plants in the dark hours before dawn. The desert is cold and still. The stars begin to fade. Far out at sea, a bank of fog forms above the cool water and drifts inland on a slow breeze. It moves silently across the dunes and the stones. The lichens, the air plants, the long-leaved Welwitschia all stand ready. They do not move. They do not call out. They simply open themselves to the air, and the air gives back what it can. Researchers have begun to wonder if the lessons hidden in these plants might one day help dry communities elsewhere. Large mesh nets have been hung on coastal hills in Chile and Morocco to catch fog the way a tillandsia leaf does. The nets work, sometimes very well, but they never quite match the patient efficiency of the plant itself. itself, why a tiny scale of leaf tissue can collect water more reliably than a hand-built net, is a question scientists are still slowly answering. For now, the fog rolls in and rolls out. The plants drink and wait. Somewhere in the soft chemistry of their leaves lies an old secret about how to live with almost nothing for a very long time. The desert keeps that secret close and shares only small pieces of it with those who watch carefully. The cactus lives by a clock that moves slowly. So slowly, in fact, that a single saguaro standing tall in the Sonoran sun may be older than the country it grows in. These tall, ribbed plants of the American Southwest can live for 200 years. In their first decade of life, they grow barely an inch. A seedling no bigger than a thumbnail may need 10 years to reach the height of a teacup. Patience for a cactus is not a virtue. It is the only way to survive. This slow rhythm shapes everything about the plant. A saguaro will not grow its first side arm until it is around 70 years old. Some never grow arms at all. Others may sprout 5, 10, even 20, each one taking decades to push outward from the central trunk. The shape of an old saguaro is, in a sense, a written record of its long life. Each curve, each lifted limb marks years of slow patience under a sky that rarely rains. The cactus breathes on a different rhythm too. Most plants open their tiny leaf pores during the day. They drink in carbon from the air while the sun feeds them light. But in a desert, the day is too hot. Opening those pores under the noon sun would mean losing precious water with every breath. So the cactus does something strange. It waits. It keeps its pores closed all day, sealed against the heat. Only after the sun sinks does it open them, drinking in the cool night air and storing the carbon for the next morning's quiet work. This nighttime breathing is called crassulation acid metabolism, a long name for a simple trick. The plant has shifted its entire daily cycle to match the kindness of darkness. The yearly cycle is just as careful. The saguaro blooms only briefly, often for a single night in late spring. White flowers open at the top of the tall column, glowing softly under the moon. Bats arrive in the dark to drink the nectar. the time the sun rises, the bees and the small desert birds take their turn. By the following night, each flower has already begun to close. A whole year of waiting, gathered into a few hours of bloom. The fruit that follows is red and full of tiny black seeds. A single saguaro may release tens of thousands of seeds in a season. Almost none of them will live. Most are eaten. Most that escape being eaten will dry out in the sun before they can root. Of all those thousands, perhaps one will find the right spot, the right shadow, the right wet year, and begin the slow climb upward. The cactus invests in patience and in numbers, scattering seeds into the dry wind and trusting that somewhere the odds will turn. Researchers who study these plants have noticed something curious. Saguaros do not appear in steady, even-aged groups. Instead, whole stands seem to share birthdays. A grove may hold many plants born within a single wet decade, with very few from the years before or after. This suggests that saguaro reproduction is tied to rare combinations of conditions that may come only once every 20 or 30 years. What exactly triggers a good saguaro year remains an open question. Some scientists point to ocean temperature cycles in the distant Pacific, which can shift rainfall across the Southwest. Others wonder whether long underground water tables, slow to refill, play a role we do not yet measure well. The truth may lie in some quiet combination of both, or in factors we have not yet identified. Other desert plants follow even stranger rhythms. The creosote bush of the Mojave can clone itself outward in slow rings, with some clonal rings believed to be more than 10,000 years old. The plant in the center dies. New stems rise from the edges. The ring widens year by year, century by century, like a slow pulse spreading across the desert floor. Whether the oldest of these rings truly count as a single living thing, or as many short-lived bushes sharing one ancestor, is a quiet philosophical puzzle that botanists still debate. So the desert keeps time differently than the green places of the world. Its clock is measured not in seasons, but in decades. Not in days, but in nights. A cactus that grew during the reign of a forgotten emperor may still stand in the dry air tonight, taking the cool breath of the desert, and the question of what wakes the seedlings in their rare and scattered birth years remains, like so much else in these dry lands, beautifully unresolved. Beneath the cactus and the quiet stone, in the cracks of dry soil and the thin shade of low shrubs, there lives a hidden population. It is a population of seeds. Some of them have been waiting there for years. Some have been waiting for decades. A few, perhaps, have been waiting even longer than that. They lie still in the warm dust, sealed in their tough little coats, holding their tiny green futures inside them. They are not sleeping in any ordinary way. They are pausing, and the question of how long they can pause and what finally wakes them is one of the gentler mysteries of the desert. The desert floor, if you could lift it up and shake it, would rain seeds. Ecologists call this hidden layer the seed bank. It is the desert's quiet memory. Every wildflower that bloomed a generation ago, every grass that dried in the wind, has left tiny offerings behind. The wind buried them. The ants carried them. The rain pushed them into the cracks. And there they wait, in their thousands and millions, just below the surface where your foot would fall. What is remarkable is how long they can wait. In some dry regions, researchers have coaxed seeds to sprout that were many decades old. There are reports, still debated, of seeds germinating after a century or more. The exact upper limit is not fully known. Each species has its own patience. Some seeds need only a single good rain. Others seem to require a particular set of conditions before they will stir. The desert holds them all in the same quiet drawer. How does a seed know when to wake? This is where the mystery deepens. A seed cannot see the sky. It cannot watch the clouds. And yet, somehow, it must distinguish between a brief sprinkle that will quickly evaporate and a real, soaking rain that might give it a chance to grow. If it guesses wrong, it dies. If it waits too long, it also dies. The cost of a mistake is total. One theory is that seeds measure the depth and duration of moisture in the soil around them. A light shower wets only the top layer and dries away within hours. A true storm pushes water deeper, and that deeper wetness lasts longer. Certain chemicals in the seeds coat may dissolve water soaking happens. Once those chemicals wash away, the seed is free to sprout. Another idea is that some seeds count cool nights and warm days, a kind of inner calendar that helps them recognize the right season. There are also seeds whose coats are so hard that nothing short of a small flood will crack them. Some need to pass through the gut of a desert animal before they can grow. Some need fire. Some need the slow grinding of sand against their shell, year after year, until the coat finally thins. Each strategy is a different bet on what the future might bring. The neighbors of these seeds are part of the puzzle. Ants gather them and carry them down into cool underground chambers where the temperature stays steady and the moisture is gentle. Rodents stash them in scattered piles and forget some of them, planting tiny gardens by accident. Birds eat them and drop them far away. Lizards push past them. Beetles tunnel around them. The seed bank is not a still place. It is a slow community, busy in ways too small and too quiet for us to easily see. And the plants themselves seem to coordinate in their own patient way with this hidden layer. A single shrub may drop seeds for many years before a generous rain finally arrives. When that rain does come, the desert can change overnight. Hillsides that looked bare for a decade burst into color. Flowers no one in the area has seen in their lifetime suddenly appear. Some of those flowers come from seeds that were already old when the gardener's grandmother was a child. What still puzzles researchers is how a seed knows it has waited long enough, or whether it knows at all. Is the long pause an active state, with the seed quietly monitoring the world? Or is it more like a slow, slow countdown, with chemistry simply ticking down at its own pace? The honest answer is that we do not fully know. Different seeds may do it differently. Some may be patient by accident. Others may be patient on purpose. For tonight, picture the dust beneath a dry hillside. Picture the millions of small green sleepers tucked into it, each one holding its own private clock. Some are listening for rain. Some are listening for fire. And some, perhaps, are simply waiting for a season that has not yet come. Somewhere in the dry places of the world, there lives a small mouse who may never take a single sip of water in its entire life. The kangaroo rat of the American Southwest is one of the strangest survivors on our planet. It can live its whole life without drinking, not from a stream, not from a puddle, not even from a single dewdrop on a leaf. Instead, this small, sand-colored creature makes its own water from the dry seeds it eats. Deep inside its body, a slow chemical process turns the food into tiny amounts of moisture. Its kidneys are unlike almost any other animal's. They squeeze every last drop from its food before letting anything go. Its urine comes out nearly dry, like a pale crystal. Its breath barely carries any moisture at all. The kangaroo rat does not stop there. During the burning daylight hours, it stays sealed inside a cool burrow beneath the sand. It plugs the entrance with loose soil, trapping the small puffs of humid air that come from its own breathing. The burrow becomes a tiny cave of moisture, hidden from the sun. When night falls and the desert cools, the rat comes out to gather more seeds, hopping on its long back feet across the silver sand. How its body learned this trick, no one fully understands. Some researchers think the ability evolved slowly, over millions of years, as the deserts of North America dried out around its ancestors. Others wonder if there are still hidden steps in the process we have not yet measured. The kangaroo rat is small and quiet, and it keeps its secrets well. It is not alone in this quiet talent. The fennec fox of the Sahara, with its pale fur and oversized ears, can also live for very long stretches without drinking. It pulls almost all its moisture from the small lizards, insects, and roots it catches at night. Its huge ears are not only for hearing the soft scuffle of prey beneath the sand, they also act as silent radiators, letting heat escape from its blood into the cool night air. The oryx, a tall, pale antelope of the Arabian and African deserts, has its own strange skill. It can let its own body temperature rise far higher than most mammals could survive. On a brutal afternoon, its blood may grow hot enough that another creature would collapse. But the oryx walks calmly on, conserving water by not sweating. A special web of fine blood vessels near its nose cools the blood before it reaches the brain. The brain stays safe while the rest of the body simmers. Insects, too, have found their own answers. The Namib desert beetle climbs to the crest of a dune in the early morning when fog drifts in from the distant cold ocean. It tilts its small black body forward, raising its back into the mist. Tiny bumps on its shell catch droplets of fog. The water runs down narrow channels straight into the beetle's mouth. A drink sipped from the air itself. Engineers have studied this beetle for years, hoping to copy its design. They have built fog-catching nets and water-gathering panels inspired by its shell. Yet the beetle still does it better. Exactly how its surface manages to grab water from such thin mist remains an active question. New papers are still being written about it. The beetle, for its part, simply drinks and goes on with its mourning. In the salt pans and stony plains of Australia, the thorny devil lizard does something stranger still. Its skin is covered in fine grooves, almost too small to see. When the lizard steps onto wet sand, or when dew settles on its spiny back, the water travels through these grooves by capillary action. It flows uphill against gravity, all the way to the corners of its mouth. The lizard drinks through its skin. Each of these creatures has solved the same puzzle in a different way. Each lives in a place where water is rare, precious, and sometimes entirely absent. Yet they thrive. They raise young. They hunt. They sing in their own quiet ways across the long desert nights. What we do not fully know is how many other animals out there have quiet tricks of their own. The deserts are vast, and many of their smaller residents have barely been studied. There may be beetles, mice, and reptiles in the dry corners of the world whose strange survival skills remain entirely unknown to science. For now, the kangaroo rat sleeps beneath the sand. The beetle waits for fog. The lizard drinks from its own skin. And somewhere, perhaps, an animal we have never named is doing something even stranger, alone in the dark. When the sun finally slips below the horizon, the desert begins a quiet transformation that few travelers ever stay long enough to witness. The sand, which only hours before could burn the soles of bare feet, starts to release its heat into the open sky. There are no clouds to hold that warmth in place. is very little moisture in the air to trap it. The desert exhales its heat upward, and the temperature begins to fall. In some of the hottest places on Earth, a day that reached 45 degrees Celsius can drop to near freezing before dawn. The difference between noon and midnight can be more than 30 degrees. That swing happens almost nowhere else in the natural world. A rainforest barely shifts a few degrees between day and night. A coastal city is held steady by the slow patience of the sea. But the desert, dry and open, has nothing to slow the cooling. It simply lets go. Scientists call this the diurnal temperature range, which is just a long way of saying the gap between day heat and night cold. The reason it is so wide in deserts comes down to one quiet truth. Water holds heat. Air without water cannot. The dry desert sky is like a thin blanket with 1,000 holes in it, and the warmth pours straight through. There are subtle textures to this nightly cooling that most people never notice. Sand cools faster than rock, so the dunes grow cold, while nearby boulders stay warm for hours. Small animals know this. A lizard pressed against a stone in the middle of the night is borrowing heat that the stone gathered all afternoon. By dawn, that stone is finally cool, and the lizard has moved on to find another. The whole desert becomes a slow exchange of warmth between bodies and surfaces. If you were to lie very still in the open desert at night, you would feel something strange against your skin. The air just above the sand is colder than the air at the height of your shoulders. Cold air is heavier, so it sinks and pools along the ground. In low valleys and dry washes, this cold air gathers in slow rivers you cannot see. Some researchers think these invisible currents help shape where certain plants grow and where small animals build their burrows. The map of the cold is still being drawn. Frost can form in places where, only hours earlier, the heat shimmered above the rocks. In the high deserts of Central Asia, in parts of the American Southwest, in the cold corners of the Sahara, thin white crystals appear on stones at dawn. They melt within minutes of the first light. For the briefest window, a desert plant can drink frost the way a forest plant drinks rain. Some biologists wonder whether certain cacti and lichens have quietly evolved to harvest this nightly gift. The question is open, measuring something that vanishes so quickly is harder than it sounds. Under a microscope, the surface of a single grain of desert sand reveals more pattern than the eye can hold. Each grain is pitted and scratched from a long history of collisions. Wind has rolled it against its neighbors 1 billion times. Some grains carry a thin coating of iron oxide, which is what gives many deserts their warm red color. Others are nearly pure quartz, glassy and clear. A handful of sand from one dune can contain a quiet record of where each grain came from, what mountains it once belonged to, what rivers carried it before the rivers themselves dried up. The cold nights also bring out scents the daytime hides. Certain desert shrubs release their oils only when the air drops below a certain temperature. Walk through a sagebrush flat at midnight after a cool day, and the air carries a soft, resinous perfume that simply is not there at noon. Why some plants do this is not fully understood. One idea is that cool air holds scent molecules longer, allowing pollinators that fly at night, like certain moths, to find the flowers more easily. Another is that the cold itself stresses the leaves, and the oils are simply leaking out. Both may be partly true. Above all of this hangs a sky so clear and so dark that the stars seem to press down on the dunes. Desert air, dry and dust-free in the high cold of midnight, is some of the most transparent on Earth. Astronomers have long sought out these places for that reason, and yet, looking up, what we notice most is not the brilliance of the stars, but the deep, settled quiet of a land that has spent the day burning, and now, gently, gives all that fire back. The first people to truly know the desert hunters were not scientists. They were the desert dwellers themselves. For thousands of years, nomadic peoples across the Sahara, the Arabian sands, the Kalahari, and the dry country of Central Australia watched the small predators that moved through their world. They knew which lizard could be safely held and which one could not. They knew the scorpion that hid under the flat stone and the snake that buried itself in the soft sand with only its eyes showing. This knowledge passed from elder to child by word and by careful pointing, long before any book recorded it. Drylands in the 18th and 19th centuries, they often missed what the local guides had known for generations. European naturalists arrived with nets and jars, expecting to find life in the cool of the day. They walked the dunes at noon and saw almost nothing. The sand seemed empty. They wrote back to their academies that the desert was a place of stones and silence, with only a few stubborn plants holding on. The guides knew better. They knew the desert wakes at dusk. They knew to turn over the right rock at the right hour, to read the small curling tracks at dawn, to listen for the dry rustle that meant a hunter was moving. Slowly, the naturalists began to learn this too. They started walking at night with paper lanterns. They started digging into burrows. The desert they had called empty began to fill with creatures. One of the earliest careful studies of desert lizards came from the work of European and American zoologists in the late 1800s, who collected specimens across North Africa and the American Southwest. They were puzzled by what they found. Many lizards seemed to vanish completely during the hottest months. Some species were known only from a single specimen for decades, then suddenly appeared in great numbers after a wet spring. The animals seemed to come and go on a schedule the visitors could not read. The scorpions were even more mysterious. They were hard to see in daylight, and the early collectors often missed them entirely. Then, by accident, a researcher in the 1940s noticed something strange. Under a certain kind of ultraviolet lamp, the bodies of scorpions glowed a soft blue-green. The dry, dark desert floor lit up with small, bright shapes that had been invisible a moment before. Suddenly, anyone with the right lamp could walk a stretch of sand at night and count scorpions by the dozen. Why scorpion shells glow in this way remains an open question. Some researchers wonder if the glow helps them sense moonlight. Others suggest it may help them avoid the surface on bright nights. The answer is still not settled. The silent hunters of the desert taught the early naturalists patience. The sidewinder snake, which moves across loose sand in a strange looping motion, was studied for years before its method of travel was fully understood. Films taken in the 1950s, frame by careful frame, finally showed how small parts of the snake's body touch the sand at any moment. This let it cross hot ground without burning itself. The discovery came not from a single moment of insight, but from slow, repeated watching. The fennec fox, with its huge ears and pale fur, was known to North African peoples long before it was described in European books. When it finally entered the scientific record, naturalists could not agree on why its ears were so large. One idea was that the ears helped it hear small prey moving beneath the sand. Another was that the ears released heat, cooling the body in the burning air. Both ideas are likely true in part. The full answer is still being studied. What the history of desert discovery shows, again and again, is that the dry lands give up their secrets slowly. The animals are small. They are quiet. Many of them have spent millions of years learning not to be found. The early outsiders had to unlearn the habits of the green world before they could see anything at all. They had to listen to the guides. They had to walk at night. They had to wait through long, empty days for the brief hour when life moves. Even now, new species of desert lizard and scorpion are being described every year. Some of them have been hiding in plain sight, in valleys that researchers have crossed many times. The desert keeps its small hunters well. How many more wait under stones we have not yet turned, in burrows we have not yet found, is a question no one can answer tonight. Of all the creatures that have learned to live where rain forgets to fall, the camel may be the most quietly astonishing. Most of us picture the hump and assume it holds water, the way a canteen holds a long, cool drink. The hump holds no water at all. It holds fat. A single full hump can carry up to 35 kilograms of stored energy. A slow, private pantry rising from the spine. When food is scarce, the camel draws on that fat, and the hump softens and droops to one side like a deflating cushion. A hungry camel can be read at a glance, simply by the slump of its own back. The water then lives somewhere else. It moves through the blood, through the tissues, through clever little corners of the body that the desert has shaped over millions of years. A thirsty camel can drink more than 100 liters in about 10 minutes, refilling itself like a slow, patient cistern. In most most other animals, drinking that much water that quickly would be dangerous. The red blood cells would swell and burst, but the camel's red blood cells are oval, not round, and they can stretch to more than twice their normal size without breaking. No one is quite sure how the cell walls hold so well under that pressure. The chemistry is studied, the structure is mapped, yet the precise reason these tiny oval cells can survive such swelling is still being worked out. The nose is another quiet piece of engineering. When a camel breathes out into the hot, dry air, the inside of its long nasal passages cools and traps the moisture from each breath. The exhaled air leaves the body already dried, the water saved and reabsorbed. A camel loses far less water with every breath than almost any other large mammal. Some studies suggest the nose can pull moisture even from the dry, incoming desert air at night. When the temperature drops and the inner lining becomes a kind of cool sponge, the full mechanics of this exchange are still being measured, and researchers are not entirely settled on how much water the camel truly harvests from its own breath. The body temperature drifts in a way that would alarm a doctor in any other species. A human stays close to 37 degrees Celsius, day and night. A camel allows its body to swing from around 34 degrees in the cool morning to over 40 degrees by late afternoon. By letting itself warm slowly, the camel avoids sweating until the heat becomes truly extreme. Sweat costs water, so the camel simply absorbs the heat like a stone in the sun and releases it slowly through the cold desert night. This loose internal thermostat may save the animal several liters of water every single day. The feet are wide and soft and split into two broad toes joined by a tough pad. The pad spreads under the weight, the way a snowshoe spreads on snow, and the camel can walk over loose sand without sinking deeply. The same foot does not blister easily on stones that grow hot enough to cook an egg. The eyes carry 3 eyelids. 2 move up and down. The third, thin and translucent, sweeps sideways across the eye like a soft windshield wiper, brushing away sand while still letting in light. The nostrils close to slits during a sandstorm. The ears are small and lined with hair that filters the grit. Then there is the matter of food. A camel will eat thorny branches, dry shrubs, salty plants that most other animals refuse, even bones if it must. The mouth is lined with tough fleshy bumps called papillae, which guide spiny food past the soft inner cheeks without tearing them. Some researchers wonder whether the camel's gut chemistry plays a role too, drawing more moisture from low-quality fodder than other grazers can. The exact details of that internal water harvest remain partly hidden, locked inside a digestion that is famously slow and famously stubborn. For all these wonders, the deeper question lingers. Why this particular shape, this exact set of solutions, in this exact animal? Other desert mammals have found other tricks. The camel's combination of oval blood cells, moisture-saving nose, drifting temperature, and fat-storing hump appears nowhere else in quite the same arrangement. Some scientists believe these traits arose slowly as ancestors moved across drying lands in the long, cold ages of the past. Others suggest the camel's lineage stumbled into the right corner of biology almost by chance. The story is partly written in fossils and partly still missing. The animal walks on, calm and tall, carrying its quiet secrets across the dunes. Lift your eyes now gently from the hot sand and the patient cactus and look up. Above the burning floor of the desert, the sky is rarely empty. A vulture turns in a slow circle, riding a column of warm air that rises from the baked stones below. A tiny hummingbird hovers near a single red flower, its wings a soft blur. A pale owl drifts on silent feathers across the dusk, hunting the small creatures that creep out when the heat fades. The desert is not only a place of sand and stone. It is a place where the air itself is a kind of road, and the birds above are part of one great breathing system. Think about how the sun makes that road. Each morning, the sun climbs and warms the desert floor. The rocks and sand heat up faster than almost any other surface on Earth. That heat rises in invisible chimneys called thermals, gentle towers of warm air lifting straight up into the cooler sky. A vulture or an eagle does not need to flap. It simply spreads its wings and lets the warm air carry it higher and higher. From a great height, the bird can scan miles of ground for a small movement, a flash of fur, a bone in the sun. The desert feeds the bird with its own heat. This connection runs deeper than it first seems. The thermals that lift the vulture also lift dust and tiny seeds and small insects far above the dunes. Some scientists wonder how much desert dust travels this way each year, drifting on high winds across whole oceans. We do know that dust from the Sahara reaches the rainforests of South America, carrying minerals that feed the soil there. The question of how much life depends on this slow dust river remains open. The desert may be quietly feeding forests it will never see. The birds are part of that traffic too. Some are travelers, passing through on long migrations between continents. A small warbler may rest for a single morning in a dry wash, sipping dew from a leaf, before lifting off again toward a distant green country. Others are residents, born and raised in the dry land, never seeing rain for years at a time. The roadrunner moves on quick legs across the open ground, eating lizards and snakes and beetles. The sand grouse flies long distances each dawn to find water, soaking it into the soft feathers of its belly and carrying it home to its chicks. The bird itself becomes a small flying well. Everything ties together in ways that are still being mapped. The seeds that wait in the soil are spread in part by birds who eat them and carry them in their bodies for miles. The flowers that bloom briefly after a rain are pollinated by hummingbirds and bats and small desert bees. The shrubs that grow in the shade of a cactus depend on shade the cactus makes, and the cactus depends on birds that drink its fruit and drop its seeds in new ground. Pull one thread and others move, yet how tightly woven this cloth truly is, no one fully knows. There is a quieter connection too, one that reaches up into the sky and out into weather itself. The hot air rising from a desert pushes high into the atmosphere, where it cools and spreads sideways for thousands of miles. Some researchers think these vast rising currents help shape the path of monsoon rains far away, in lands that may seem to have nothing to do with the desert. If the desert grows hotter, or larger, or smaller. The rains on the other side of the continent may shift in answer. The exact size of that shift is still debated. The fact that it happens at all is something we are only beginning to understand. And under it all, the birds keep turning in their slow circles. The owl returns at dusk. The vulture finds its perch on a ledge of sun-warmed stone. The hummingbird tucks into a thorn-protected nest, no larger than a thimble. A long-eared fox steps out from its burrow and watches the sky, and the sky watches back through the patient eye of a hawk. Each creature is doing its small part in a system far larger than itself. The heat of the sand becomes lift. The lift becomes flight. The flight becomes seed, and pollen and water carried from one place to another. The desert breathes slowly, in a rhythm we have only partly learned to read. How much of that rhythm still hides above the burning floor is, for now, a question the wind keeps to itself. For most of the year, the desert wears a single coat. Pale gold, dusty brown, the soft gray of stones bleached by long sun. The ground looks bare. The hills look quiet. A traveler could walk for days and see only the same patient palette of sand and rock and sky. Then a rare storm passes through. The clouds gather, dark and heavy, and the rain falls in a way the desert has not felt for months, or sometimes years. And within days, the bare ground answers in a way that still surprises the people who study it. The desert blooms, not in small patches, but in long, sweeping carpets of color: yellow, pink, lavender, white. Whole valleys turn into soft fields of flowers, as if a hidden garden had been waiting all along under the dust. In parts of Chile, the Atacama Desert, one of the driest places on Earth, can break into pale blooms after a single wet winter. In Southern California, the slopes of certain valleys can fill with poppies so bright they can be seen from far above. In Namibia, in Australia, in the deserts of the American Southwest, the same quiet miracle plays out whenever the rain finally arrives. The seeds that produce these blooms have been there the whole time. They sit in the soil, sometimes for years, sometimes for decades, waiting. The mystery is how they know when to wake. A little rain is not enough. A short drizzle would coax them up, only for the dry sun to kill them within days. So the seeds have learned, somehow, to measure the rain. They wait for a deep soaking, the kind that signals a real wet season before they begin to grow. How exactly they measure it remains an open question. One idea is that a chemical coating on the seed slowly washes away with each rain, and only after enough water has passed does the seed finally allow itself to sprout. Another idea is that the seed senses the depth of moisture in the soil around it. A third possibility is temperature. The cool, damp ground after a real storm feels different from the brief chill of a passing shower. The seeds may read all of these signs at once, in ways researchers are still working to understand. Even more puzzling is the way the blooms seem to shift from one year to the next. In some seasons, one species dominates. The whole valley turns gold with one kind of flower. In another year, after a similar rain, a different species takes over. The valley turns purple instead. Why one seed wakes while its neighbor stays asleep is not fully known. Some researchers wonder if the seeds take turns by design, each waiting its own length of time, so that the species does not all bloom at once and exhaust the soil. Others think the answer lies in small differences in the storms themselves, in temperature, in timing, in the angle of the late winter sun. The blooms do not last long, a few weeks at most. The flowers open, the insects find them, the seeds form, and the desert dries again. The carpets of color fade back to dust. The new seeds fall to the ground, and the long wait begins once more. A single seed may sit in the soil for 10 years, 20 years, or longer before its turn comes around. Some seeds found in old desert soils have been shown to still sprout after a century of dormancy. How long they can truly wait remains uncertain. These blooms are also changing. Climate patterns shift, and the rains that the seeds depend on no longer arrive on the same schedule. In some deserts, the great blooms are coming more often, fed by warmer ocean currents that send unusual storms inland. In other deserts, the rains are growing rarer, and the blooms are slipping away from living memory. People who remember the desert of their childhood sometimes describe valleys that have not flowered in their lifetime, whether the seeds in those soils are still alive, still waiting, is not always known. There is something quietly comforting in the thought of all those sleeping seeds under the bare ground, under the cracked clay and the loose sand. An enormous patient garden lies waiting. Most of it will never bloom in any one year. Most of it will wait through dry seasons we will never see. Yet it is there, dreaming through the heat, holding the colors of a future spring inside small dark shells. How long it can keep waiting, and what wakes each seed in its own quiet hour, are questions the desert still keeps to itself. There are places in the desert where the ground is so flat, so white, and so still that the sky seems to fall down and rest upon it. These are the salt flats. They are the floors of lakes that vanished long ago. The water dried away in the slow heat of centuries, and what it left behind was a vast pale crust of minerals, glittering under the sun like a frozen sea. Walk out onto one of these places at midday, and the light becomes something almost solid. It bounces up from the salt and down from the sky, filling the air from every direction. There are no shadows to soften the world. The horizon shimmers and wavers. Distant mountains seem to float above the ground, lifted by layers of heated air. Travelers have written about feeling weightless in these places, as if they were walking across a mirror laid flat upon the earth. When rain does fall on a salt flat, something quiet and strange happens. A thin sheet of water spreads across the surface, sometimes only a finger deep, sometimes only the thickness of a coin. That water, perfectly still and perfectly shallow, becomes the largest natural mirror in the world. The sky doubles itself. Clouds drift below your feet as well as above your head. The line between earth and air dissolves. A person standing in the middle of such a place can lose all sense of which way is up. The Salar in Bolivia, high in the dry mountains of South America, is the most famous of these mirrors. It covers more than 10,000 square kilometers of pale crust, all of it within a hand's breadth of perfectly level. Beneath that crust lies brine, a salty water rich in lithium and other minerals. Geologists believe the Salar was once part of a great ancient lake that filled the high plateau tens of thousands of years ago. That lake slowly evaporated, leaving its dissolved minerals behind as a gleaming white skin. There are similar floors scattered across many of the world's drylands. The salt pans of the Kalahari, the white sheets of Utah, the cracked basins of Central Australia, and the dry hearts of Central Asia. Each of them is the ghost of a body of water that no longer exists. Some held lakes the size of small seas. Others held only seasonal pools. The mystery, in many cases, is exactly how big these ancient lakes were, and exactly when they dried. The light tells part of the story. The minerals left behind are different at different depths of the old lake bed. Pale gypsum here, gray clays there, ribbons of carbonate elsewhere. Each layer caught the sunlight of a different age. Researchers read these layers like the pages of a faded book, trying to learn when the rains were heavy and when they faded away. The story is not finished. There are gaps in the record and theories that compete with one another about why these lakes filled and emptied in the patterns they did. One idea is that wobbles in the Earth's tilt slowly shifted the paths of rainstorms across the continents, soaking some regions for thousands of years, and then leaving them to dry. Another idea is that changes in the great ocean currents shifted moisture across the globe in long, slow pulses. A third idea is that local mountains rose or fell, blocking and unblocking the paths of clouds. The honest answer is that all three may be partly true in different places at different times. The full picture remains an open question. At night, the salt flats take on yet another kind of light. Without trees, without buildings, without dust, the stars overhead seem closer than anywhere else on Earth. The white crust reflects their faint glow softly upward. Visitors describe a feeling of being suspended inside a quiet bowl of light, surrounded by sky in every direction. The temperature drops quickly once the sun is gone, and the salt sometimes crackles softly as it cools. There is one more puzzle that lingers about these places. Tiny living things, strange salt-loving microbes, survive in the brine just below the crust. Some can sit dormant for years, then wake when a thin rain returns. Researchers are still asking how how these organisms endure such extremes, and whether the deep salt layers might hold cells far older than anyone has yet confirmed. Each new sample raises new questions. Each new question reminds us how much the bright stillness of a salt flat can hide. So the salt flats lie there in their pale light, holding the memory of vanished lakes, holding tiny lives inside their crystals, holding the sky in a single shallow mirror after the rains. Their brightness is a kind of patience. We do not yet know all that they remember. On the surface of the driest stones in the world, a thin, dark coating waits in silence. It is called desert varnish. You can find it on the cliffs of the American Southwest, on the boulders of the Gobi, on the wind-scoured rocks of the Sahara and the Negev. From a distance, the varnish looks like spilled ink that has dried in slow streaks down the cliff face. Up close, it shines a little, a quiet metallic sheen of brown, black, and rusty orange. This coating is one of the great small mysteries of the Drylands. It is incredibly thin. A layer thick enough to see may take 10,000 years to form. Some patches on ancient stones are believed to be far older than that. And yet, for all the centuries people have looked at it, no one is fully certain how it grows. Desert varnish is mostly made of clay, with smaller amounts of manganese and iron mixed in. The manganese and iron are the parts that puzzle scientists. There is far more of these metals in the varnish than in the rock beneath it, and far more than in the dust that settles on the rock. Something is gathering them, concentrating them, painting them onto the stone in slow, patient strokes. The question is what? One idea is that tiny living things do the work. Certain bacteria and fungi can pull manganese out of dust and air and bind it to surfaces. In this view, the varnish is a kind of slow biological signature, a stain left by countless generations of microbes living on bare rock under the desert sun. Researchers have found microbes living on varnished stones. Some studies suggest the metal layers do match the way these organisms feed. Another idea is that the varnish forms without life at all. In this view, ordinary chemistry does the work. Dust lands on the rock. Dew arrives at night. Sunlight and heat trigger slow reactions that bond manganese and iron to the clay, building up a film one molecule at a time. Some experiments have produced varnish-like coatings in the lab without any living thing involved. The question remains open. The varnish may be biological, chemical, or some quiet partnership of both. We simply do not know. What makes desert varnish even more curious is the sound that is sometimes hidden inside it. Long ago, people across many deserts pecked images into the dark coating to reveal the lighter rock beneath. These carvings are called petroglyphs. They show animals, hunters, spirals, handprints, and shapes whose meanings are now lost. Some of them are thousands of years old. When the wind moves across a varnished cliff covered in these images, the rock can hum softly, the way any large stone surface hums in moving air. Visitors have described a low, breathy tone, as if the cliff itself were exhaling. The sound is not magic. It is simply air moving over an uneven face of stone. But standing before a wall covered in ancient marks, listening to that quiet hum, it is easy to feel that the varnish is keeping time in a language we have not yet learned to read. There is another sound bound up with the mystery, though it is too slow for our ears. If the varnish truly grows one atom at a time, then each layer is, in a sense, a recording. It captures the dust that fell in a given century. It captures the chemistry of the air. It captures, perhaps, the rhythm of wet years and dry years stretching back into deep time. Some researchers have begun to read these layers the way others read tree rings, hoping the varnish might whisper the climate history of places where no trees grow. Whether that whisper is reliable is still debated. The varnish does not grow at the same speed everywhere. It may pause for long stretches and then resume. Two stones a short walk apart may carry very different records. The science of reading desert varnish is young, and the rock is patient. For tonight, it is enough to picture the scene. A cliff of red sandstone, washed in the soft light of late afternoon. Dark streaks running down its face like slow tears of ink. A faint hum in the moving air. And somewhere within the thin coating, a quiet argument that has not yet been settled between microbes and chemistry, between life and stone, between the question, desert keeps the Varnish. The Varnish keeps its secret. And the wind keeps moving across the cliffs, carrying a sound so soft you almost have to imagine it to hear it at all. There is a sound the dunes sometimes make, a low, rolling hum that seems to come from everywhere and nowhere at once. Travelers have heard it for centuries in the great sand seas of the world, in the Gobi, in the Sahara, in the deep dunes of Oman and the Mojave. The sound can last for minutes. It can rise as loud as a small engine, deep and steady, like a distant cello played by the earth itself. For a long time, no one could explain it. The old caravans had their own stories. They spoke of buried bells, of spirits singing in the dry places, of voices carried up from cities lost beneath the sand. The mystery had a name in many tongues, but no real answer. Then, slowly, the numbers began to whisper something back. When researchers measured the singing dunes, they found a strange thing. The hum was not random. It held a clear musical note. In some dunes, the note was close to a low G. In others, it was a steady F sharp. The pitch was so pure that it could be matched on a piano. A whole hillside of loose grains, somehow, was singing in tune. The math behind it turned out to be quietly beautiful. The sound depends on the size of the grains, the speed at which they slide, and the depth of the dry layer near the surface. When the grains are nearly the same size, and when they tumble at the right pace, they begin to move together. They bump against one another in time. Millions of tiny collisions fall into a shared rhythm, and that rhythm becomes a tone. In a way, each dune is a kind of instrument. The avalanche is the bow. The grains are the strings, and the pitch is set by a simple ratio between grain size and grain speed. Change the grain size, and the note changes. Make the grains a little larger, and the pitch drops. Make them a little finer, and the song climbs higher. This is the elegance of it. A desert that looks chaotic. All those countless grains shifting in the wind turns out to be running on quiet rules. The same rules that govern a violin string or a bell. Mass, motion, and timing. 3 small numbers that hold the whole song together. The dunes follow other patterns too. Their shapes are not accidents. A crescent dune, with its two graceful horns pointing downwind, forms only when the wind blows steadily from one direction and the sand is sparse. A star dune, with arms reaching out in several directions, forms where the winds shift through the year. Each shape is a kind of equation written in sand. Wind speed, wind direction, sand supply, and time, all balancing into a form. The spacing between dunes follows rules of its own. In many sand seas, the large dunes sit at fairly regular distances from one another, like ripples on a vast, slow pond. The spacing depends on how high the dunes are and how the wind moves over them. Bigger dunes sit farther apart. Smaller ones crowd close. The same kind of pattern shows up in snowdrifts, in river sandbars, in the ripples on a beach at low tide. The same simple math repeating at every scale. And still, the singing itself holds open questions. Researchers can describe the conditions that make a dune hum. They can match the pitch to grain size with surprising accuracy. But they do not fully agree on why some dunes sing easily while others, with seemingly identical sand, stay silent. One idea is that a thin, dry surface layer acts as a kind of speaker, amplifying the vibrations from below. Another idea is that the grains themselves need a certain smoothness, polished by long ages of wind before they can fall into rhythm. The evidence points in both directions. So the math gives us part of the answer and leaves part of it open. That is the quiet pleasure of this kind of science. The universe does run on simple rules. A dune is a counting problem. A song is a ratio. A shape is a balance of forces that can be written on a single page. And yet, when you stand at the foot of a humming dune at dusk, with the sand still warm and the sky going soft and pink, the math does not feel like math. It feels like a voice, a patient, low voice that has been singing this same note in this same key for longer than any human has been alive to hear it. We understand the notes. We do not quite understand the singer. And tonight, that gentle gap is a fine place to rest. For thousands of years, people have lived in the driest places on Earth. They did not just pass through. They built homes, raised children, told stories, and grew old under the same hard sun that kills lesser visitors in a single day. How they managed this is one of the quieter wonders of human history, and it rests on a balance so delicate that even small changes can undo it. Consider the people of the Sahara. Long before the dunes spread as wide as they do today, the region held lakes, rivers, and green pastures. Cave paintings in the rocks of the Tassili Plateau show swimmers, cattle, and tall grasses. Then slowly, over thousands of years, the rain pulled back, the lakes dried, the herds moved south, and the people who stayed had to learn a new way of living, one tuned to scarcity rather than plenty. That learning is still not fully understood. Researchers wonder how quickly the old ways gave up to the new. Some think the change took centuries. Others think it came in sharp jolts, with a single dry decade tipping whole villages into a different life. The dust layers in old lake beds hold clues, but the clues do not all agree. What did emerge in many parts of the world were lives built around the small mercies of the desert? The Bedouin of Arabia followed thin lines of grazing from one well to the next. The San of the Kalahari learned to find water inside hollow roots, and inside the bellies of certain melons. The Tuareg of the Central Sahara wrapped their faces in long indigo cloth, both to keep out the sand and to slow the loss of moisture from their breath. Each adaptation was tiny. Together, they made the impossible possible. The balance, though, was always thin. A single dry year could empty a well. A shift in the wind could bury a pasture in sand. People who lived this way learned to read the land with a care that city dwellers rarely match. They knew which dune would shelter a tent from the night wind. They knew which clouds carried rain and which carried only dust. They knew the songs that helped a tired camel walk one more hour. This knowledge passed from parent to child across countless generations. And here lies another open question. How much of that older knowledge still survives, and how much has quietly slipped away as roads and trucks and cities have come closer to the old desert paths? Some researchers worry that whole libraries of desert wisdom are being lost faster than anyone can write them down. Others believe the knowledge is more stubborn than it looks, hidden in family stories and daily habits that outsiders simply do not see. The fragile balance is not only social, it is also written into the land itself. A desert soil can take a century to form a thin crust of living microbes, lichens, and tiny mosses. That crust holds the surface together and lets a little water sink in instead of running off. One careless footprint can break it. One vehicle track can scar it for decades. The desert looks tough, but in many ways, it is one of the slowest healing places on the planet. Wider forces press in as well. The amount of rain a desert receives depends on the spin of the planet, the warmth of distant oceans, and the angle of the sun. Shift any of these even slightly, and the rain belts move. A village that has thrived for 1,000 years may suddenly find its wells running dry. A pasture that fed goats for centuries may turn to bare stone. Earth gives no promises that the conditions of yesterday will hold tomorrow. What strikes many who study desert peoples is how much they understood this fragility long before modern science arrived. Their songs spoke of cycles. Their proverbs warned against greed at the well. Their customs spread the use of pasture across many families, so no single patch was worn down. They lived inside a system they could not fully see, yet they treated it with a respect that suggests they could feel its edges. Whether that wisdom can guide the modern world through its own dry years is still unknown. Some hope it can. Some fear it is already too late. The desert itself keeps its own counsel, indifferent to our questions, patient with our slow learning. For tonight, it is enough to picture a small fire under a wide sky, a circle of quiet faces, and the soft murmur of a story being told once again, the way it has been told for longer than anyone remembers. Somewhere beneath the sand, there may be cities no living person has ever seen. The deserts of our world cover such a vast area, and they shift so slowly across the centuries that whole settlements can vanish under them. We have found some of these lost places. We have only guessed at others, and many more, almost certainly, still wait in the dark beneath the dunes. The desert is patient in the way it hides things. A wind that lifts only a thin layer of sand each year can. Over 1,000 years, bury a stone wall completely. A river that dries up can leave its old towns stranded in a sea of dust. Over centuries, the dust deepens. The roofs collapse. The streets fill. And then the desert simply moves on as if nothing had ever been there. One famous example is the lost city of Ubar, sometimes called the Atlantis of the Sands. For a long time, it was known only from old stories and a few faded mentions in ancient texts. Then, in the early 1990s, satellite images of the Arabian desert showed faint lines in the sand, old caravan tracks pressed into the ground long ago. All seemed to lead to a single point. When archaeologists dug there, they found the remains of an old trading site, possibly linked to the legend. Whether it is truly the city of the stories remains an open question. But the lines in the sand were real. This is the strange power of the desert. The very dryness that buries things also preserves them. Wood does not rot the way it would in a wet forest. Cloth and leather can last for thousands of years. Bones, pots, and seeds wait under the surface in a kind of slow sleep. When a dune finally rolls away, what it uncovers can look almost untouched by time. The Taklamakan Desert in Central Asia has given up some of the most surprising finds. Beneath its shifting sands, explorers have found the remains of old towns along a forgotten trade road. They have found mummies with red and blonde hair, dressed in woven cloth, their faces still visible after thousands of years. Who these people were, where they came from, and how their settlements fell silent are questions still being slowly answered. Each find raises new ones. In the Sahara, rock paintings show a green land that no longer exists. Giraffes, hippos, cattle herds, swimmers. The pictures suggest that only a few thousand years ago, parts of the Sahara held lakes and grasslands and busy human communities. Where did those people go when the rains pulled away? Did their villages get buried whole? Or did they fall apart slowly as the wells ran dry? Some old hearths and tools have surfaced where dunes have shifted. But most of that lost world, if it is down there, has not yet been found. The Gobi has its own quiet secrets. So does the Atacama. So do the smaller deserts of North America and Australia. In each, every shard pushed up by a windstorm, a line of stones that seems too straight to be natural, a shape in a satellite image that no one can quite explain. Each hint is a small open door. What makes this mystery so gentle is that it does not need to be solved tonight. The sand is not in a hurry. The buried walls are not going anywhere. They have waded through dynasties and droughts, and they can wait a little longer. Modern tools are starting to help us peer through the surface. Ground-penetrating radar can sense buried structures without a single shovel. Satellites can spot faint patterns in vegetation or soil color that hint at old foundations below. Some researchers wonder whether we are on the edge of finding many more lost places. Others think the truly large discoveries are rare, and that most of what lies below will stay below for a long time yet. There is something soothing about that uncertainty. The desert is not a closed book. It is a slow one. Every storm rewrites a page. Every shifting dune turns a corner. Somewhere out there, under a quiet ridge of sand, a doorway may be lying on its side, half buried, waiting for the wind to expose it. Somewhere else, a whole street may rest beneath the dunes, its stones cool, its corners sharp, undisturbed for 1,000 years. We do not know how many lost cities the deserts hold. We do not know whose voices once filled them, or what stories they told before the sand grew tall around their walls. The question stays open, and the sand keeps quietly moving above whatever lies beneath. The drylands are moving, not quickly, not in any way you could see by standing still and watching, but moving all the same. Across the edges of the great deserts, the dry ground is creeping outward, gaining a little here, losing a little there. Scientists call this slow shift desertification. It means land that once held grass and small trees is becoming bare and dry. The question of why it spreads and how fast and whether we can slow it remains one of the open puzzles of our time. Some of the spread comes from the climate itself. As the air grows warmer, the patterns of rain shift in ways that are still being measured. Certain regions get less rain than they once did. Other regions get the same amount of rain, but the heat dries the soil faster. The result, in many places, is the same. dry earth where green earth used to be. Some of the spread comes from people. When too many animals graze a fragile patch of grassland, the roots weaken. When too many trees are cut for firewood, the wind has nothing to break it. When the topsoil blows away, the desert takes one more small step. Researchers still debate how much of the spread comes from climate and how much comes from these human pressures. The honest answer seems to be that both matter and that they feed each other in ways that are hard to untangle. Picture the southern edge of the Sahara, a wide band called the Sahel, where the great desert meets the dry savanna. Satellites have watched this border for decades. In some years, it pushes south. In other years, it pulls back, and green returns. The boundary breathes. No one can say with full certainty where it will sit in 100 years. One theory is that warming will dry the Sahel further. Another is that shifting monsoon patterns may, in some places, bring more rain rather than less. The evidence points different directions in different valleys. Now stretch your mind much further. 1,000 years, 10,000. The deserts we know today are not permanent features. They have grown and shrunk many times across deep time. The Sahara itself was green only 6,000 years ago, filled with lakes and rivers and grazing herds. Cave paintings still show the animals that lived there. The wet Sahara faded as the planet's tilt shifted slowly, and the rains moved south. One day, perhaps, the rains will move back. The slow wobble of Earth's axis will keep dancing, and the green Sahara may return long after the cities of our age have crumbled. 1,000,000 years from now, the map of the Drylands will look nothing like it does tonight. Continents drift on the slow currents of the mantle below. Africa is creeping north, closing the Mediterranean inch by inch. Australia is moving toward the equator. Mountain ranges that block rain today may erode into low hills, letting moisture pass. New mountains will rise where there are now plains, casting fresh rain shadows behind them. Each shift will birth new deserts and erase old ones, push further still into the deep future, 1,000,000,000 years ahead. The sun grows slowly brighter as it ages. Long before it swells into its final form, its rising warmth will change the oceans and the air. Some models suggest that far in that distant time, the seas may begin to thin, and the whole face of the planet may drift toward dryness. The dunes may inherit places where forests once stood. The salt flats may grow wider than seas. These are projections built on physics, not predictions of any certain day, and much remains uncertain about how life and weather will adjust along the way. But within that slow drying, new things will form too. New minerals will crystallize in the brine. New patterns of dune will rise where none have stood before. Perhaps new forms of life, shaped by heat and thirst, will move across that altered ground. The desert is not an ending. It is one of many faces the planet wears between its long sleeps and its long awakenings. For now, in our own short slice of time, the question is gentler and closer. How much of the spreading can we slow? How much green can we hold? Whether the Sahel will breathe outward or inward in the lifetime of a child born tonight, the answers are not yet written. They sit in the soil, in the rain that comes or does not come, in the patient roots of grasses that are deciding, season by quiet season, whether to hold on. When we say the word desert, most minds reach for sand, golden dunes, a hot sun, a line of camels against a pale sky. But the true meaning of the word is quieter and stranger and much wider than that. A desert is simply a place where water is rare, and by that gentle measure, some of the largest deserts on Earth are not warm at all. They are made of ice. Antarctica is the largest desert in the world. It is colder than almost anywhere else on the planet, and it is also one of the driest. In some valleys there, snow has not fallen for thousands of years. The wind sweeps the rock clean. The ground is bare and frozen. The sky above is often clear and pale. If you stood in one of those dry valleys and closed your eyes, you might feel the same hush that travelers describe in the Sahara at dawn. Different temperature, same silence, same long absence of rain. The Arctic, too, holds vast cold deserts. The high plains of Central Asia, the dry stone fields of Patagonia, even parts of the high Andes, where the air is so thin and the rain so rare that the ground cracks like old pottery. All of these are deserts, truest sense of the word. They are places shaped by what is missing, and when you see them that way, the dry world grows much larger than we usually imagine. This is the strange shape of the question we have been sitting with. Deserts are not really about heat. They are about thirst. They are about the way water moves or fails to move across the skin of a planet. And once you see that, you can step back even further. You can ask where the water came from in the first place. You can ask why this world has any rain at all. The water in the desert spring, the water in the cactus, the water in the camel's slow blood, the water in your own quiet breathing tonight. All of it is very old, older than the dunes, older than the mountains. The hydrogen in every drop was made in the early universe, long before the earth existed. The oxygen was forged inside stars that lived and died before our sun was born. Those stars cooked light atoms into heavier ones, and when they ended, they scattered the new atoms into the dark. Some of those atoms drifted and gathered and became the cloud that became our sun and our planet and the seas and the rivers and the slow underground water beneath the Sahara. The calcium in the bones of the desert fox came from dying stars. The iron that paints the red rocks of the Australian outback came from dying stars. The carbon in every dry thorn, every cactus spine, every grain of pollen waiting in the cracked soil came from the same ancient furnaces. The desert is not separate from the sky. It is the sky settled and cooled and arranged into stone. Even the sand itself carries this long story. Quartz grains are made of silicon and oxygen, both born in stars. Each grain has been part of a mountain and a river and perhaps a sea floor before the wind found it and rolled it into a dune. A single handful of desert sand holds material older than the planet beneath your feet. And the wind that shapes that sand is driven by the sun, which is itself a star, quietly turning its hydrogen into helium and light. So when a small lizard crosses the dunes at twilight, when a beetle tilts its back to catch the fog, when a seed waits in the dust for a rain that may not come for 30 years, all of that patient living is made of starlight, rearranged. The desert is one of the places where this becomes easy to feel. there is so little in the way, so little noise, so little green, so little hurry, just stone and sky and the long arithmetic of time. And still, after all of this, we do not fully understand the dry places of our own world. We do not know all the creatures that live in them. We do not know all the cities that may sleep beneath their sand. We do not know how far they will spread, or whether the cold deserts will grow warmer, or whether new ones will be born. The mystery is not solved. It has only grown wider and quieter and more beautiful the longer we have looked. Tonight, the dry lands keep their secrets, and the stars that made them keep watch. And so we come to the quiet end of our long walk through the dry lands. The dunes stretch out behind us in the soft dark, their ridges curved like sleeping animals. The stones rest where the wind has placed them. The salt flats shine faintly under a thin moon, pale and still, holding the memory of water that left long ago. Think for a moment of how much we have wondered about tonight. We sat with the question of why some lands forget the rain. We listened in our minds to the low hum of singing sand. We watched seeds wait in the soil for years, holding their small green secret. We thought about cities buried somewhere beneath the dunes, and about lizards that drink with their feet, and about varnish painted on stone by something we still cannot fully name. None of these questions are closed. That is the gentle truth of it. The desert keeps more than it shows. Every grain of sand is a small piece of an older mountain, ground down by patient wind. And every grain has traveled farther than most of us ever will. The desert does not hurry, and it does not answer quickly. It simply waits, the way it has always waited, while researchers walk its surface with notebooks and instruments, asking soft questions of the heat and the cold. Picture the planet now from very far above, the way a slow camera might see it. The blue oceans curve across one side. The green forests gather near the middle, and the deserts trace their long pale bands across the continents, soft gold and rust and white, like brush strokes laid down by a careful hand. Africa carries the Great Sahara. Asia holds the Gobi and the empty quarter of Arabia. Australia keeps its red center. The Americas hold the Atacama and the Sonoran and the Patagonian drylands, even the poles where they're cold deserts of ice. Together, they cover nearly a third of the land. A third of our world is quiet in this particular way, and the planet turns. It turns slowly under its thin sky, carrying all of these dry places through night and back into morning. Somewhere right now, a fennec fox is curling into the cool sand at the mouth of its burrow. Somewhere, a saguaro is holding the day's water inside its tall green body, swaying just slightly in a breath of wind. Somewhere a beetle is climbing a ridge to catch the fog on its back. Somewhere a grain of sand is being lifted, set down, lifted again, on a journey that no one is counting. The mysteries we touched tonight will still be there in the morning. The lost cities will keep their silence a little longer. The varnish will keep painting itself slowly on stones no one has yet found. The aquifers will keep holding their ancient water beneath the dunes. The seeds will keep waiting. The drylands will keep their slow spread, and the people who love these places will keep walking them, learning what they can, leaving what they should. There is something kind about a world that holds onto its secrets. It means there is always more to wonder about. It means the curious mind never runs out of quiet questions to carry into sleep. The desert, with its long memory and its soft horizons, is a good teacher of patience. It reminds us that not everything needs to be solved tonight. Some things are simply meant to be wondered about gently while the body rests. So let the dunes go on without you for a while. Let the stones cool under the stars. Let the salt flats shine, and the cactus bloom, and the small creatures move through the cool dark on their small, careful errands. The planet is turning, and you are turning with it, held by the same slow gravity that holds the sand in place. The night is wide. The morning will come in its own time. You are small, and the world is vast, and that is a comforting thing tonight. The same wind that shapes the dunes is moving softly somewhere near your window. The same patience that grows a cactus is in the slow rise and fall of your breath. The same quiet that fills the desert at night is here, in this room, settling around you like a soft blanket. Rest now. The dry lands will keep their mysteries for another evening. There is no hurry there has never been any hurry. The sand will sing again tomorrow for someone, somewhere, and the wondering will go on. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet dreams.